thank you. Yeah, so thank you very much for still being here, I guess, and for being in this session. And yeah, to just say a few words to me, to myself, I'm working at the Alfred Wegener Institute in Bremerhaven, which is the Helmholtz Center for Polar and Marine Science. And this is a software that I want to present here, which is in collaboration with people from the GEOMA, the Helmholtz Center for Ocean Science in Kiel. And I will present and say a few design choices we made to develop the ESM-Tools, which is a software to run and build climate models. Maybe. Yeah. So as a motivation, as I said, this tool is a workflow tool to build Earth system models and to run climate simulation on different HPC computers. And the aim is that it provides to the climate researcher an easy-to-use tool to have an easy way to start actually doing climate research with climate models. And so the target user group is actually climate researchers that just start to work with climate models, or also more experienced scientists that can use this to make their work a bit comfortable, because, as I will show, it can be a bit getting complicated, or at least the variety of models that you can use and the different HPCs can make it, a bit not complicated, but lots of options to choose. So we started to develop this software a few years ago, and at some point we made choose a different language. So we switched actually from shell functions to Python, and we did a few design choices to make the tool more modular with respect to the code development, but also to respect to the usability. So it's extendable and it's interoperability. Sorry, to enhance the interoperability and to have a more maintainable software. So just to give you an impression what this actually does, the software. So it's, as I said, a modular workflow and infrastructure software for Earth system models. And just to show what an Earth system model is, it's a model that anyway. So it can be a system of different model components that can be, for example, an ocean model and an atmospheric model, and these are then coupled together to build a system of the Earth. And here are two examples of models that are developed at the Alfred Wegener Institute, which are basically similar, but they use different components. For example, they use the same or a little bit different version of an ocean model, FESOM, which is also developed at the RVN, but they use different atmospheric model in the setup. And in order to be a system, then these compartments need to be exchange data, of course, because there's an interaction from the ocean to the atmosphere. And for that, you can also use software that couples fields that they need to exchange, and this is in this case OASIS, and this also comes in different versions. So, and this is just two examples, so there are many other climate models or ocean models around, and atmospheric models that you may want to combine and run simulations with. Okay, and just to give you an impression of what the output of such a climate model is, so you can run different scenarios with such a coupled system. This is an example for RVCM3, which just shows on the left the temperature anomaly from 2 different model simulations that have 2 different scenarios included with respect to CO2 emissions. And this, I think it's a mean over the last 25 years. And you see how the change in air temperature is due to the CO2 emission increase, because this is a difference to a model, reference model simulation that assumes CO2 emissions from pre-industrial times. And on the right, there's the same example for precipitation. So just to give you an impression what we're doing with these models. That's not. No, no. So maybe to start from the researcher perspective, if you want to do climate research and you think I want to run simulations, then you can say I need to choose a model that suits my research field, and if you have chosen a model, or maybe decide to use different models because you want to compare them, you'll need to, depending on your project, what HPC resources you can use, depending on your project, maybe where you have applied for computing time. And because there are different HPC resources, you have to see what actually are the software libraries that are available, and this can make the whole thing for each model that you may want to use not complicated but complex, let's say it this way. So here's again an example for just 2 models or setups or systems that you may want to use. On the top there's RVCM 1 or 3 or any other climate model you may want to use, and then you can choose from different HPC resources. And because all these ESM models, they come with different components that need to be built differently, maybe because they are also developed at different institutes, so it's not that all of these components are developed at the same institute. So they all come with different build infrastructure, and also with different run script that actually runs the simulation. So then now come the ESM-Tools into play, which one tries to put all these different, options under actually one tool. So one. Okay. So we have ESM-Tools is basically consists of 2 commands. So the ESM master is to build the model and each component in it, and so the aim is that you just have an easy way of sorry, I don't know, the pointer's not working, to call ESM master for several models the same way. Oops. Oh. Can you go? Okay, can you go back? Yeah, so that for every model that you actually want to run simulations with, you have the same call for the build process, and you also have the same call for running the model, and all the description of what should happening for what period. For example, you want to run the simulation that's in the ESM run script command, you can describe with a YAML file, and there are other arguments. So you can, for example, give it a name, your experiment, and others. So I don't want to go into details. That you basically don't have to care so much about what different models are built differently. So you just use this tool, and from that there are some software requirements that we want to enable actually. So as I said, you have to address different models and HPC requirements. We want to have this easily extendable. because maybe some researchers want to include new ESM or new model components into the tool, and also include other HPC resources they may want to use. And so it needs to be customizable by the user, and who also maybe not have not a background in computing and or coding. And one, I think the main issue here is that we want to do this as much as possible without changing the source code. Yeah, thanks. So then now this is just the main focus here on my talk. So I want to show where we have this modularity, and it's basically in the code development, and we try to make the usage also modular or extendable. Mm-hmm. So for the development of the code, we separate code and configuration. So you configure your HPC resources, for example, independently from the source code. So then when you add HPC or an ESM model to the tool, you can do this by just changing or adding configuration files to this. And and in order to make this a bit more functional, we developed a parser that it's parsing the YAML files, so the configuration files, and I will show in an example how this looks like to give this more functionality. And we also have an adaptable workflow manager, so then you can add additional functionality to the whole tool. Yeah. So maybe this is the source code. It's modular. It's basically different Python modules. And yeah, I can skip this. So what's maybe more important is that we have for each component and for each model setup in HPC resources, there is its own configuration file. And if you want to add something, HPC resource, you can add then or change also YAML files that already exist, or take information out of that and add to this. So this is the way the user can add a model and the HPC resource to the tool. And we have applied a certain hierarchy of the configuration files. So because you can set all these variables also in your run file, this actually runs the simulation. This will win over the others that are set in the other configuration files. And this is just an example of the parser, so the additional functionality we want to apply to the configuration files. And maybe the most important is on the lower right. So you can actually have kind of if statements in the YAML file, and it's like these choose blocks, so you can set a variable, and depending on that, you can, in the same file or even in another file, you can actually set other variables that are depending on the first variable you set. And we have some variables that you can use from different configuration files, and like some math or calendar operation. And so now I come to the adaptable workflow manager. So this is, if you run a simulation, you have to prepare your experiment. This is done in the prep compute phase, so to say, and then the main computation of the simulation takes place, and then you have to clean up a bit, and then depending on your setup, you may restart the whole simulation again, because you run this in chunks of 1 year, for example. And this is so each of these phases is actually a Python module, and what actually happens during this step is like prescribed in kind of a recipe. Okay. And you can actually, can you just one more? So you can add either a function call to the recipe, so then you have to change the code a bit, or you can, this can also be coming from a different Git resource. And can you, once more, you can actually add a completely new phase to the whole process, and in this case you can also add a shell script, so there is the possibility to not changing the code, but to add functionality to the tools. Yeah, can you? So this is the last two slides. So yeah, we see, of course, an advantage of develop the code in a modular way, and the ability that users can actually add something to the functionality or add new ESMs with only changing the configuration file. We see this in the pull request that a lot of changes are actually focused on the change in the, sorry. Yeah, maybe the next slide is a bit more, yeah, can you, just the last one, sorry. So maybe the challenge is that because we applied this syntax to the YAML file, and the user asked for this needs to be very good documented, and to add the functionality to the workflow, it needs really good examples. This is something that users also demand, and yeah, good error messages, of course. And what actually is also important, since there can be a lot of changes in the configuration file, that we have good integration tests, that the whole system is not breaking. And now I stop. Okay, thank you very much. Yeah.